Okay, so typically what we'll have is we can usually take objects and look at them as beams. Assuming that's true, we'll do some free body diagrams for beams and then use that to compute stress, which then will go in a later chapter to compute the to create the design. So let's review this. So first step is draw a free body diagram, and I'll do an example. So you this is something you'll understand with an example. The second step is we'll assign a coordinate frame. And the third step is apply equations of static equilibrium. Okay, we are only looking at two-dimensional free body diagrams, which means we only have to deal with these three equations. The net force in the x direction is 0, the net force in the y direction is 0, and the net moment, this is typically about the z-axis, which comes out of the plane of the paper, is 0. Okay, so when we talk about beams, these beams have to be supported in some way or the other. There are different ways in which beams can be supported. One is a roller support. Here, there's a beam. Okay, and I'm just going to show a section of the beam. So it's not, we're not interested in what's happening on the right side. So there's a cut. Here is a roller. This is the ground. So there's a ground, there's a roller on that, and on top of there's a beam. And for something like this, you're told to draw a free body diagram, essentially the reaction forces. So what you'll do is you'll isolate the beam from the roller. You'll replace the effect of the roller using a force. And a roller can only transmit a force in the normal direction. So it's like there's a roller, there's a contact, right? It can only apply a force this way. Okay, now there could be a force in the sliding direction if there's friction, but we assume there's no friction. So a roller only transmits a vertical force. Okay, another common support system is a pin or a bearing. Okay, a pin or bearing will typically shown this way. Cut. So now we need to draw a free body diagram for the bearing. Okay, now when you isolate the bearing, a bearing will induce forces in both directions, a vertical direction as well as horizontal direction. So we need to show that with a vertical force, a horizontal force, like so. It's not important. I mean, you could assume any direction you want. You could put V as downwards, H to the left. It doesn't really matter. When you do the math will tell you the right direction. So don't worry about that. So you could draw it this way if you like. You could also, if you think this is easier, you could also show it as some force, reaction force acting at an angle theta, right? This is also a valid way of showing a reaction force. So here, clearly, H and V are related. H, V, R are and theta are related. H is R cosine theta, V equals R sine theta. So you could assume this way or this way. It's up to you. If you do it either way, you can relate the two. So if I ask you to find H and V, but you prefer doing it using reaction force R at an angle theta, you solve it using R and theta, and then convert that to H and V using this formula. So it really doesn't matter how you do it. Okay, so those are the two kinds. There's a third kind, a fixed support. 1, 2. So a third kind. So this will be a fixed support. Here it's actually sort of entrenched into the wall or ground. Okay, so for such a case, again, you'll pull it off from the wall. Then you'll show the reaction forces. There'll be a vertical force, there'll be a horizontal force, and because the way it's fixed to the wall, it'll also the wall will also resist bending, so there'll be a moment. There are three unknowns here: h, v, and a moment. Again, you can write h, v, or you can write r at an angle theta. Okay, so a free body diagram means that the object should be free. When I say free, it's now connected to the wall. You need to isolate the wall from the body. So I drew that. And then you replace the effect of the wall with forces, right? The forces and moments, like I wrote down earlier. So because it's a wall, we would have three forces, well, two forces: a vertical force, a horizontal force, and a moment. Okay, that's the reaction force. We also need to put in the point load, and then there's also a weight, which we assume that's uniformly distributed. So this is going to be exactly midway of the beam. So this weight is 100 kg, but there's gravity 9.81, so it's going to be 981 newtons. And for length, this is 1. This should be 3 meters. Okay, so this question, I'm not really asking you to uh, compute h, v, and m, but you can clearly do that by writing those three equations. So that will be the next question. Okay, for a problem like this, where you're told to compute the reaction forces, uh, my goal is to follow the three steps I talked about. Okay, so I'm going to follow these three steps. Draw a free body diagram, assign a coordinate frame, apply equations of static equilibrium, and then you'll have the forces which you're trying to solve for. So step one is draw a free body diagram. So isolate the beam from the supports, replace the effect of the supports with reaction forces. So on the left side is a roller. So that will only induce a vertical reaction force. On the right side is a bearing that will induce two forces. One would be in the vertical direction, let's call that VB. Another one, the horizontal direction. Okay, I'm randomly assuming the directions here. You can assume it the other way too, which is down or up, whatever you want. Okay, let's put all the other forces. There's a 200 Newton force here. So 100 Newton force. Now there's a 600 Newton force acting at an angle of 45 degrees. I could keep it that way, but just to make my life easy, I'm just going to compute its components in the vertical and horizontal direction, because that will actually make it easy to write the equilibrium forces. So the 600 Newton force, I'm going to draw it as resolve it. So 600 times cosine of 45, it's 600 divided by square root of 2 is actually 424. So this will be the horizontal force, and the vertical force will be 600 sine of 45, which is same 6 square root 2, which also will be 424. So I have 424 acting down, 424 acting to the right. And that's pretty much what I have for the free body diagram. Mm. Okay, second step is to assign a coordinate frame, which I don't need to really do it separately. I just can just show it like this: x, y. Okay, and the third step is to write the equations of equilibrium. So net force in the x direction is 0. So we look at the free body diagram, we identify all the forces in the horizontal direction. There's only one force, which is HB, and the way HB is drawn, it's drawn to the left. So it's going to be minus HB equals 0. And so HB is 0. Oh, sorry, my bad. My bad. HB is negative, and then there's 424, which I completely forgot. 424 equals 0, right? 424 acts in the positive direction, HB acts in the negative direction. So this gives me HB is 424 newtons. The next, let's write Fy equals 0. We have VA, which is acting upwards, but upwards is positive. So VA 424 acts downwards, so it's negative. 100 acts downwards, so it's negative. 200 acts downwards, so it's negative. VB acts upwards, so it's positive. Okay, so if you try, you cannot solve for VA and VB because you have one equation and two unknowns. So I'll just write an expression involving VA and VB. So VA plus VB is, if you sum it up, it's 724. Okay, last equation is moment about, well, when you talk about moments, you need to take moments about some point for a two-dimensional problem. You have a lot of options here. You could take moments about just about any point. You could take moments about A, you could take moments here, you could take moments there. It's just about any place you could take moments. The trick here is to take moments at a point where maximum number of forces arrive, right? That way you eliminate the most number of unknowns in the equation. So in this case, we have two forces at B and one force at A, but we already computed the force HB. So this, I would just recommend choosing this point or this point, because when you choose a moment point, any of those, you'll eliminate that particular force because the moment about that point is going to be 0. So let's just choose moment about point A equals 0. Okay, so we have so VA would have a contribution of 0 because it passes through A. So we have 424. The two 424s is one 424 acting down, and that's at a distance of 2 meters. So 424 times 0.2, that's the magnitude, sorry, 2 meters, right? And then we need to figure out the direction. Now, about A, if 424 acts, it's going to induce a clockwise moment. A clockwise moment is considered negative. So it'll be negative 424 times 2. Okay, similarly, we have 424 acting to the right. So 424 acting to the right. Its moment arm is, well, we assume that this VA is actually at the point, at the midpoint. And so 424 is at a distance of 0.2, right here, 0.2. So the magnitude is 424 times 0.2. So this is A, this is 0.2. So you can see that 424 also leads to a clockwise movement, so it'll have a negative sign. Okay, then we have 100 Newton force, a 100. So its distance from the point A is 3 plus 2, which is 5. So its magnitude is 100 times 5. But then it's creating a clockwise moment too about point A. So it's with a negative sign. Okay. Then we have 200, which is at a distance of 2 plus 3 plus 2, which is 7. You can argue that just like the 100 Newton force, it's going to induce a clockwise torque, so it's negative. Okay, and there's one more left, which is VB. VB acts counterclockwise. Well, it acts upwards first. So VB is upwards. Its distance is again 7. So VB times 7, that's the magnitude of the moment. But you can see that it's creating a counterclockwise torque, a counterclockwise movement. A counterclockwise movement is positive. So you just put positive, and this whole thing should equal 0 per this equation. So you can see that this equation, the last one I wrote down, has only one unknown, VB. So VB, you can solve for. I solved it. I got VB equals 405 newtons. And then when you put the value of VB in this equation, you can solve for VA. VA comes out to be 724 minus 405, which is 319 newtons.